typically throwaway devices, so if the relay malfunctions, it's best to replace the entire device. When the electric motor starts, the amperage draw is much higher than when the motor is running at full speed. The amperage that a motor draws when it's up and running is often called the full load amperage, or FLA. The amperage that the motor draws on initial startup is called locked rotor amperage and can be in the range of 5 to 7 times greater than the full load amperage. For the motor shown here, the full load amperage is 2.6 amps, so the locked rotor amperage will be in the range of 13.0 to 18.2 amps. The current relay opens and closes its contacts depending on the amount of current that is flowing through the run winding of the motor. The current relay is made up of a low resistance coil and one set of normally open contacts. This is the schematic for a current relay. The coil of the relay is wired in series with the running winding of the motor and is connected between the R and L2 terminals. The normally open contacts of the relay are connected between the start terminal S and L2. When the motor is initially energized, the starting winding is not in the circuit and the motor will not be able to start. The motor cannot start because there's no starting torque being generated. The motor is now drawing locked rotor amperage. The motor now draws locked rotor amperage, which generates a strong magnetic field that pulls the normally open contacts closed, energizing the start winding. Once the motor begins to operate, the current draw of the motor falls from locked rotor amperage to the full load amperage, causing the normally open contacts to open once again. Once the starting winding has been removed from the circuit, the motor will continue to operate with only the running winding energized. A relay commonly used on single-phase CSR motors is the potential relay. This relay opens and closes its contacts depending on the induced voltage produced by the start winding. When the motor is energized, the start winding experiences not only the line voltage being supplied to the motor, but also an induced voltage that's generated in the winding. As the motor picks up speed, the amount of induced voltage increases. When this induced voltage rises to a predetermined set point, the contacts on the relay will open, removing the start winding from the circuit. The potential relay is made up of a high resistance coil between terminals 2 and 5, and a normally closed set of contacts between terminals 1 and 2. The coil of the relay is wired in parallel with the starting winding. The normally closed set of contacts is connected between the start terminal and the start capacitor. When these contacts open, the start capacitor will also be removed from the circuit. When in the open position, a CSR motor will run as a permanent split capacitor motor. When the motor is initially energized, both the running capacitor and the starting capacitor are in the circuit. Since the motor is just beginning to run, the induced voltage in the starting winding will be low and the contacts on the relay will remain closed. Potential relays are rated by 3 voltages. The pickup voltage is the voltage at which the normally closed contacts open. The dropout voltage is the minimum voltage that's required to keep the contacts open. The continuous coil voltage is the maximum voltage at which the coil can continuously operate. The potential relay and start capacitor can also be used to aid motors with starting problems. For example, a PSC motor can be converted to a CSR motor with the aid of a hard start kit, which is comprised of a potential relay, current relay or PTC device, and a starting capacitor. The advancement of solid-state controls has produced another type of current sensing relay, the positive temperature coefficient or PTC thermistor. The PTC is made of a ceramic material that has a low resistance at low temperature. As the temperature of the material rises, Due to the current flow through the device, the resistance increases rapidly until no current can pass through it. The device is installed in series with the start winding of a split phase or capacitor start motor. On startup, current flows through both the starting and running windings of the motor. The PTC acts as a small starting capacitor in the sense that it helps provide the torque needed to start a motor. The current flow causes the resistance of the PTC to increase. This increase in resistance reduces the amount of current flowing through the start winding until no current flows through it at all. The resistance of the PTC typically ranges from 5 ohms when cold to over 100,000 ohms when heated. The motor will continue to operate as a split-phase motor with only the run winding energized. When used on capacitor start motors, the PTC is wired in series with the start capacitor. These devices require anywhere from 3 to 10 minutes to cool down, so they're not the best choice for applications where the motor short cycles. In addition to the PTC starting device, a universal electronic motor starting relay has been introduced that can be used to replace both potential and current sensing devices. This device uses a time function instead of sensing actual voltage or current and can be wired as a potential relay or as a current relay. Just as with the PTC, the electronic motor starting relay is wired in series with the start winding on either split phase or capacitor start motors. Overloads are designed to open if excessive current is sensed in the circuit they are intended to protect. Relays and contactors cause sets of electrical contacts to open and close in response to the voltage applied to the coil of the device. The current relay opens and closes its contacts depending on the amount of current flowing through the run winding of the motor. Potential relays, often used on capacitor start, capacitor run motors, open and close their contacts depending on the induced voltage across the start winding of a motor.